Hi, in this sketch we will see how we can control a servo motor. A servo motor is pretty much a geared DC motor that has an angle of rotation from 0 to 180 degrees, and we are going to control that using a potentiometer. And a potentiometer is going to give you an analog value, and based on that analog value, or how you turn the knob, we are going to see how the servo motor position is going to be varied from 0 degrees to 180 degrees. So as you can see, we are now going to connect our servo motor to pin number 2. The pin number 2 is also analog pin, which can give a pulse width modulated signal. So based on the pulse width of the signal, the servo will be able to go from 0 to 180 degrees. So as you can see, there's some material here. So in practice, we need to make sure that we have a pulse width from 0.5 to 2.5 milliseconds. So by giving a pulse width of 0.5 milliseconds, you can make the servo to go to position 0. And similarly, when you give a pulse width of 2.5 milliseconds, and then you can make it to go 180 degrees. So any pulse width in between will make it to be between 0 to 180 degrees. So that's what is defined here. So you can see that we defined the servo pin as pin number 2, and then you have a minimum pulse of 500, a maximum pulse of 2500 initialized. So these are some of the values or variables which have been initialized here, and similarly our potentiometer is now connected to an analog pin 0, which is nothing but AD0. So here the potentiometer analog value is going to be converted into digital, and the digital value is then going to be translated into a pulse width, and the pulse width will control the position of the servo. So our setup is, as you can see, the servo pin has to be defined as an output. We would initialize our pulse to be a minimum pulse, which is going to be 500, and then we also enable our serial port at baud rate 9600. So by enabling this, it gives you a feedback like what is the position, or you can do some debugging. So the loop, as you can see, we read the analog value from the analog pin using the analog read function, and then store it into a variable integer, which is analog value. Then we use a map function, which is nothing but a translator. The translator takes in the analog value, and the analog value is represented as a 10-bit value and ranges from 0 to 1023, and that's going to be converted, depending on what values you get, that will be converted into the values between your minimum pulse and maximum pulse. So this is a very useful function which is often found. So this does a software translation of an analog value to any kind of digital value you need. So that translation is then mapped into the pulse, and as you can see, as far as we do have a condition statement here, which is pretty much defines a refresh time, because you don't want the servo to continuously refresh for, let's say, every 1 millisecond. So you want it to refresh it. So as you can see, because it's a geared system, so you want it to be in a very smooth transition. So therefore we try to do that for every 20 milliseconds. And here is what we do. We do a digital write function for your servo pin, which is high, colon for the delay of the pulse. So that would be the pulse width duration, and then for the rest of the time you drive it down low. So this pretty much defines the function from here to here, defines the period of the waveform, and by giving this you or delay in microseconds, you're trying to hold up the pulse high for that duration. So therefore that defines the pulse width. So that pretty much explains what we try to do. So we can actually hit the compile button and then upload it as we have done in other modules.